I mean, it's one thing to ask an AI to, write a polite email to your boss.
Oh, absolutely.
Right. But it's a completely different universe to ask that same technology to compose, produce, and execute a heartbreaking, mathematically perfect blues track that actually makes you feel something.
It really is. It's a massive leap.
It's huge. So today, for you listening, we're taking a deep dive into the blueprints for two really groundbreaking frameworks from the AI audio space. We've got the original LeVo and its massive June 2026 successor, LeVo 2.
Yeah, and this is where it gets fun.
Exactly. The mission of this deep dive is to shortcut your understanding of how AI is finally learning to compose full-length, high-quality songs that actually follow human instructions. We aren't just looking at how AI generates sound, we're looking at how researchers are actively quantifying subjective human taste.
Which is, frankly, an incredibly ambitious goal. I
Mm.
mean, for a long time, the AI community has kind of treated music generation as this stubborn, basically unsolvable puzzle.
Yeah, totally.
Language models conquered text relatively quickly, but translating that architecture into the audio domain required researchers to completely rethink how a machine processes creative intent.
Okay, let's unpack this. Why has it historically been so hard for a language model to write a good song? I mean, if you look at the underlying architecture, text and audio are, they're both just sequences of data.
Right, on a fundamental level, sure.
So why is full-scale music generation such a massive computational hurdle compared to, say, generating a 1,000-word essay?
Well, it fundamentally comes down to data density
Right.
and the sheer dimensional complexity of music. Think about text for a second. A single token might represent an entire word or a concept.
Okay.
The model predicts the next word and it builds a linear sentence. But audio, especially high-fidelity music, operates at something like 44,000 samples per second.
Wow, yeah.
It is incredibly dense. And beyond just the volume of data, a song is fundamentally nonlinear. I mean, it's layered. You have the melody, the rhythmic pocket, the underlying chord progressions, and the timbre of the instruments, and they're all happening simultaneously.
Right, and that's before you even introduce a human voice into the mix. Getting an AI to synthesize a voice is a pretty known quantity at this point.
Sure, speech synthesis is very mature.
But getting that synthesized voice to sing perfectly in time, lock into the key, and, embed naturally inside a multi-layered instrumental backing track, that requires a level of contextual awareness that traditional large language models just weren't built for.
Precisely. The vocal instrument harmony is the ultimate bottleneck here. And complicating all of this is the scarcity of high-quality training data.
Oh, because it's hard to find.
Exactly. You can scrape the internet for billions of text documents to train an LLM, but you can't easily scrape perfectly separated, pristine multi-track audio files to teach a system how individual instruments interact with vocals.
Right, which is exactly why this deep dive is so critical for you. Whether you're a working musician trying to keep an eye on tech, or you're just someone who loves a good playlist, understanding the architecture behind AI-generated music reveals a lot about the intersection of art and math.
Definitely. And to understand the mechanics of the June 2026 release of LeVo 2, we really have to examine the foundation it was built upon.
So going back to the first LeVo.
Right, the original LeVo tackled that basic problem of vocal and instrument coordination by introducing a highly specific data processing strategy. It essentially used two distinct types of tokens in parallel.
Right, the research describes the original LeVo as an LM-based framework relying on LLM, which is their custom language model paired with a music codec.
Exactly.
And instead of treating the audio as one massive, undifferentiated stream of tokens, LeVo processes what they call mixed tokens and dual-track tokens simultaneously.
Yeah, and that parallel modeling was the major breakthrough of the first iteration.
So how do the mixed tokens work?
Well, the mixed token basically represents the combined flattened audio of the vocals and the accompaniment together. The entire purpose of forcing the model to process mixed tokens is to achieve that harmony.
Ah,
The system has to evaluate how the voice and the instruments interact as a single unified piece of audio data.
but I mean, relying exclusively on mixed tokens creates a mud problem, right? If the AI is only looking at the flattened, unified audio, it loses the acoustic detail. It can't distinguish the sharp attack of a snare drum from a vocal transient.
That is exactly where the second type of token comes in. So, LeVo simultaneously processes dual-track tokens, which separately encode the vocals and the accompaniment. They keep the data isolated.
Got it.
So you have the mixed tokens ensuring the overarching harmony and musical alignment, while the dual-track tokens ensure crisp, high-fidelity acoustic isolation for the final output.
Oh, I see. So it's like trying to bake a cake where the sponge and the frosting have to be baked in the exact same oven at the exact same time?
That's a fun way to look at it, yeah.
Like, the mixed tokens ensure they taste good together, but the dual track tokens make sure the frosting doesn't melt into the sponge.
I love that analogy. It's perfectly accurate.
Hmm.
But of course, processing both the sponge and the frosting, or the mixed and dual-track tokens, simultaneously within a single language model usually leads to the data paths interfering with each other.
Right, because it's just too much conflicting information.
Exactly. To stop these different token types from collapsing into noise, LeVo employs two decoder-only transformers and utilizes a modular extension training strategy.
That sounds intense.
It is.
Wow.
It physically compartmentalizes the learning process within the architecture. This allows the system to update its weights for harmony from the mixed tokens without overriding the weights it learns for audio clarity from the dual-track tokens.
And looking at the source material, the results of that parallel processing were objectively impressive. I mean, LeVo was compared alongside models like Suno V4.5 and Marika O1.
And it held its own.
It really did. It excelled at full song generation, zero-shot style transfer, and highly specific text-based control. The researchers were feeding it these exact descriptions like male, bright pop, melancholic piano, or, female, loud, rock, dynamic, electric guitar, and it just mapped those semantic instructions directly onto the corresponding token layers.
What's fascinating here is that while this parallel token processing was an incredibly clever workaround for the harmony problem, it actually set the stage for a massive structural problem.
Wait, really?
Yes, the researchers built a highly effective system, but the architecture inherently capped its own potential. The very mechanism that made LeVo 1 work created a ceiling that they had to shatter with LeVo 2.
Okay, so the researchers refer to this in the paper as a structural trade-off. If parallel processing was the big breakthrough, why did it become a liability?
It comes back to how language models manage memory, specifically the attention mechanism. You see, mixed token modeling perfectly preserves vocal instrument coordination, but it obscures those track-specific details.
Right, the mud problem.
Exactly. Conversely, leaning heavily on the dual-track prediction guarantees perfect acoustic separation. But because you are processing the vocals and the accompaniment as distinct data streams, you are effectively doubling the sequence length.
Oh, wow. And transformers are notoriously fragile when you push their context windows to the absolute limit, right? Especially with something as dense as audio tokens.
Exactly. The longer the token sequence, the more the AI's attention mechanism gets diluted. In music generation, requiring these massive sequences severely weakens the model's ability to globally plan a full-length track.
So it just kind of loses the plot.
Pretty much. The system might generate a brilliant, cohesive first verse and chorus, but by the time it reaches the 3-minute mark, the context window is so stretched that the AI has literally forgotten the overarching melodic theme of the song.
That's hilarious, but also terrible for making a song.
Right. The composition just loses all coherence.
So, if parallel processing is creating a catastrophic memory bottleneck, they have to decouple the data streams. They can't process the overarching harmony and the individual acoustics at the exact same time anymore if they want a cohesive 3-minute song. So what does the June 2026 LeVo 2 architecture do differently?
They pivoted entirely. The June 2026 solution introduces LeVo 2 as a hybrid LLM diffusion framework. They abandoned parallel processing at the base level and solved the structural trade-off using a concept called hierarchical representation modeling.
Okay, hierarchical. So they broke it into steps.
Yes, 3 distinct sequential steps.
With step 1 being semantic planning, right?
Correct. The language model, LLM, first predicts only the mixed tokens. But it doesn't do this to generate the final playable audio.
What's it doing then?
It does this strictly to sketch out the global blueprint of the song. The chord progressions, the rhythmic structure, the macro-level harmony, the big picture. Because it's only processing mixed tokens at this stage, the sequence length is manageable, and the AI can maintain perfect global coherence from the first second to the last.
Oh, that's smart. Then step 2 is the track-specific refinement. Once that global blueprint is locked in, a separate track-specific language model uses that blueprint to predict the vocal and accompaniment tokens in parallel.
Exactly.
It essentially goes back in to generate the high-fidelity separated audio data based on the plan.
That's exactly how it works.
But here's where it gets really interesting, though, because I have to push back on this a bit.
Okay, go ahead.
Wait, so it doesn't just generate the song from start to finish. It's sketching the entire blueprint of the song first, and then going back in to color the vocals and instruments separately. Doesn't a track-specific LM risk undoing the harmony established in the semantic planner?
It's a very valid concern.
Like if the planner dictates a quiet acoustic bridge and the track-specific refiner decides to just, hallucinate a loud electric guitar riff because it thinks that sounds better acoustically, wouldn't the entire composition fall apart?
It would, and that is the exact vulnerability researchers face when chaining models together, but they anticipated it. To prevent the track-specific refinement from corrupting the semantic plan, LeVo 2 utilizes that modular extension we discussed earlier.
Oh, right.
Yeah, they use it to train the track-specific LM for acoustic refinement strictly while preserving the aligned semantic planner.
So it can't change the blueprint.
Exactly. The weights of the semantic planner are basically frozen as a constraint. The track-specific model is mathematically forbidden from altering the fundamental harmony. It is only authorized to enhance the acoustic quality of the individual components.
That makes a lot of sense. So this hierarchy allows LeVo 2 to resolve that structural trade-off. It gets the global coherence and long-term planning of mixed tokens, plus the stunning acoustic fidelity of dual-track tokens, completely avoiding the computational bloat that ruined long-term attention in the original model.
You nailed it.
But that brings us to step 3 of the hierarchy, which is the actual audio synthesis. Because up to this point, the AI is just predicting tokens. It hasn't actually made a sound yet.
Right, it's all just data representations at that stage.
The research states that LeVo 2 uses a diffusion-based music codec to reconstruct the full-length waveforms. How does a diffusion model actually turn those abstract tokens into a playable audio file?
Well, the underlying math is remarkably similar to visual diffusion, like Midjourney. But instead of denoising a grid of visual pixels, the music codec starts with pure Gaussian noise in a continuous latent audio space.
Okay, so it starts with static.
Exactly. Then, conditioned by the specific tokens generated by the track-specific LM, it iteratively removes that noise step by step. It sculpts that static noise into high-fidelity acoustic waveforms, reconstructing the precise frequencies of the instruments and vocals.
That is wild. So the hierarchical model solves the audio structure perfectly, but, a structurally perfect, highly detailed song can still be incredibly boring to listen to.
Oh, absolutely.
Right.
Technical execution does not equal musicality.
Right. Now that LeVo 2 has a flawless blueprint for generating the audio, how does it actually know what sounds good? How do researchers bridge that gap between structural engineering and actual subjective human taste?
This is perhaps the most significant leap forward in the LeVo 2 paper. In the original LeVo, they tackled taste using multi-preference alignment based on direct preference optimization, or DPO.
Okay, DPO.
Yeah, they used semi-automatic data construction to feed the AI static pairs of human preferences to handle diverse human tastes. It was essentially telling the model, humans rated track A higher than track B, adjust your weights to output more variations of A.
Which works, I guess, but it seems incredibly slow and limited by the size of the human preference dataset.
It was, which is why LeVo 2 completely abandons that for a massive upgrade, an aesthetics-guided training schedule.
And I have to admit, when I read how they implemented this, it kind of blew my mind. The paper details an automated music aesthetic evaluation framework that analyzes massive scales of training data during pre-training.
Yes, and it assigns what they call musicality tier conditions to large-scale data to provide musicality priors.
Wait, musicality tier conditions? That sounds like sending the AI to a strict music conservatory where it's forced to grade thousands of songs before it's ever allowed to compose its own.
That's actually a brilliant way to conceptualize it. If we connect this to the bigger picture, they are training an automated framework to recognize the statistical distributions of what human listeners generally classify as aesthetically pleasing.
So it's learning the math of good taste.
Essentially, yes. By assigning these tiers, it provides the main model with a baseline compass for aesthetic quality before preference alignment even begins.
So it ensures the AI isn't just learning the structure of music from a data set filled with, amateur garage band recordings and poorly mixed demos.
Exactly. And those musicality priors are critical for the final phase of LeVo 2's development, which is their progressive post-training pipeline.
Right. Let's break that down. The progressive post-training pipeline involves SFT-supervised fine-tuning, followed by large-scale offline DPO, and concluding with closed-loop semi-online DPO.
Yes. And note that this progressive schedule specifically separates musicality learning, controllability alignment, and acoustic refinement.
And the paper explicitly states they separated these stages to mitigate what they call optimization conflict, right?
Yes, and understanding optimization conflict is key. If you try to update the neural network weights to make the model better at strictly following a text prompt, while simultaneously updating the weights to ensure the acoustic quality is pristine, the mathematical gradients actually fight each other.
Ah,
I see. The
oh.
model might sacrifice audio clarity just to force the inclusion of a loud, distorted guitar to satisfy the prompt. Separating out these stages avoids the limitations of static offline preference pairs, allowing the AI to balance instruction following with actual melodic beauty.
So the SFT aligns the base formatting, and then the offline DPO locks in the text control. But what about that last step? How does semi-online DPO differ from the offline version?
Well, offline DPO uses a static data set,
Hmm?
but in closed-loop semi-online DPO, the model generates candidate tracks on the fly. An active reward model then evaluates those newly generated tracks against each other based on acoustics and musicality.
Oh, wow. So it's competing against itself in real time.
Exactly. It's refining its taste dynamically, and the results speak for themselves.
Hmm.
LeVo 2 outperforms open-source baselines across 6 subjective dimensions and approaches leading commercial systems on listening metrics.
It's just staggering. So what does this all mean for you? Over the course of this deep dive, we've watched AI song generation evolve from a messy clash of audio tokens in the original LeVo into a highly structured, hierarchical system in LeVo 2.
A system that fundamentally plans